trying to see if we can have an alternative way of deriving this expression here. What is the probability that the energy is EI? Okay, we made some intuitive arguments and showed that it turns out to be this expression right here, where beta is basically 1 by kBT, Boltzmann constant times temperature. And we were trying to, now we were doing something else where we took a different approach, where we considered various ensembles, each of which are in the same macro state. However, they are all in a different micro state and they are all exchanging energy with each other, and they are satisfying these constraints. Summation over AI is equal to n, where n is the total number of ensembles in the system, and summation over EI times AI is equal to E, and A suffix I means the total number of systems with energy EI. That is what it means. AI is EI. So then, in order to actually get this probability, what we essentially need is, we need the average number of systems with energy EI divided by the total number of ensembles in the system, and that would essentially give us PI. So AI is essentially the total number of average number of systems with energy EI, and if you divide it by the total number of systems present here, you would get the probability that the system has energy EI. Okay. In order to do that, we first started enumerating the various possible distributions that the system can have. So, if E1, E2, E3, E4 and so on are the various energies that it can have until EE, then A1, which is represented through this flower bracket. So, flower bracket A1 means a particular distribution, a particular way by which the system can achieve the energy, the associated energy that it is supposed to have. Okay, that is this energy. Okay, that is this energy, right? So you can have A11. The superfix 1 represents the is a label for the distribution that I am talking about, whereas the suffix here represents the energy level that is occupied by that system. So A11 means, in this example that we talked about here, it turned out to be 10, and in the second example it turned out to be 8, and so on. Right? Is this aspect clear so far? Right? So this was okay. So now, what is the total number of ways you can achieve a certain distribution? So for example, what is the total number of ways you can achieve the distribution A1 or the flower bracket A1? So that is nothing but n ensembles taken A11 at a time. So you have taken A11 of these and put it in the basket of E1. The remaining has to be put in the basket of A21, has to be put in the basket of E2, and so on. So it's basically a combination problem, right? So it's nothing but n taken A11 at a time times n minus A1, because you have removed A11 samples, times from this you are taking A21 and putting it into energy E2, and you continue to do that, and this is what you will get, right? You have studied this in your lower classes, right? Similarly, there is a different distribution. The total number of ways this distribution can be attained is given by that, and you can keep going. Consequently, the total number of ways, the probability that you can get any one particular distribution is total number of ways you can get that distribution divided by total number of ways all possible distributions can be realized, right? So that is that probability is being represented by this H. H flower bracket AK means what is the probability that I can get this distribution AK. That is what it means. Now, what do I want? Again reiterating the fact that what I essentially need is the average number of samples or systems with energy EI divided by total number of systems will give me the probability that the system has energy EI, right? So I need to find this out. How will I find this out? Let us take, for example, the average number of systems with energy E1, average number of energy E1. What would that be? That would be A11 times the probability that I can have A11 system at energy E1 plus A12 times the probability that I can have A12 systems with energy E1, and A13 times the probability that I can have the system with energy, I can have A13 systems with energy E1, and so on, which is what I have written down here. So, average number of systems with A1 is nothing but A11 times the probability that A11 systems are at energy level 1 or E1, right? A12 times the probability that so on and so on. So, now what is the probability that A11 systems are at energy level E1? It is nothing but the probability that the A1 distribution is realized, isn't it? Right? So, this is nothing but A11 times H of A1 plus A12 times H of A2 and so on. Therefore, the average number of systems with energy EI is nothing but Aij times H of Aj, and that if I divide by n, I get actually Pi, right? But still, this is still not in the form that we saw previously. We are expecting to see the same expression right here, something like e to the power minus beta E divided by summation over all possible energy states exp exponent minus beta E. That's what we are trying to see, okay, but we still don't have it. Now, what happens is that we have to make the same argument that we made several classes ago when we actually started statistical mechanics. What we said was, when the system is basically at equilibrium, there is one specific distribution of energy states that it would take, such that that particular distribution has this number to be such a large value that for that special distribution, this H or the probability that the distribution is realized is very, very close to 1. Right? We made that argument, right, when we started talking about statistical mechanics, right? So, it so happens that there is a special distribution A star such that is approximately equal to 1 or very, very close to 1, and all the other distributions are basically irrelevant or 0. So, for all practical purposes, we could consider Pi to be only that special distribution. Because H of A star is actually equal to close to 1, right? This is approximately equal to, at equilibrium, all the other H's become 0, and there is one special distribution for which H of that distribution is close to 1. So, I have Ai star divided by n, that would basically give me my equilibrium distribution. Okay. Now, the problem is we still don't have this as a function of the energy of the system, but we can get it by performing a maximization. Okay. What we say is that if the distribution that it takes is essentially the one that will basically maximize this quantity, right? If this number of ways this can be achieved is so large, then this is a very large number, and consequently that is almost close to the total number of ensembles present, and the probability that it is seen is highest. So, what we have to do is we have to maximize W of A. That means we have to find the number of systems with energy E1, number of systems with energy E2 in such a way that this quantity omega W of A is a very, very large number. Okay. So, we are working with that special, we are trying to find out that special system. We are simply throwing out all the other systems because we know that they are going to be irrelevant. Okay. There are better proofs to show that they are irrelevant, and that this distribution actually peaks about that special distribution and everything else is 0, but we are not going to do that in this class. Okay. So, we are just going to maximize this, but we have to subject to the constraints that all the AI, summation of all the AI must be equal to 1, and AI, EI must be equal to some E. Okay. So our composite function that we have to maximize is nothing but so we have to maximize with respect to what? The AIs, right? We have to find the value of AI which maximizes this entire function. So how would you maximize it? You take dou f by dou AI and equate it to 0 and keep doing A1 for dou f by dou A1, dou f by dou A2 and so on, and equate it to 0 to find the conditions that is necessary to maximize the function subject to these two constraints. Now the whole problem is when you are trying to maximize things with factorial, it becomes a problem, right, unless you use what is referred to as the Stirling's approximation. So we use the Stirling's approximation, which is excellent for when the value of n is very, very large, right. So for in Stirling's approximation, n factorial is nothing but n ln n minus n, right. So let us rewrite this based on Stirling's approximation. You will get n ln n minus n minus of summation over all I AI ln AI minus AI, right, because in each of the denominator you would have AI ln AI minus AI. Is this right? No, wait, 1 minute. I need to I think this is Stirling's approximation. Okay, so this is not Stirling's approximation. Stirling's approximation is ln of n factorial is n ln n minus n. Okay, so instead of extremizing, I made a small mistake here. Instead of extremizing this function, we need to extremize the ln of that function, right? Otherwise, it would be impossible for us to extremize it. So then you have writing this down properly, you would get n ln n minus n minus of summation over I AI ln AI minus AI, right? But this has to be minus lambda 1 times summation right. So let's do the following. Dou f by dou aj must be equal to 0, where aj is anything here. So these things don't depend on aj. Therefore, you have here minus of only the derivative with respect to the jth thing will actually survive here, right? So you will have here ln of aj plus aj plus actually plus 1 because it is going to be plus 1 minus 1, right, minus lambda 1 into minus lambda 1 minus beta into Ej, right. Is this, you are able to follow this step? Okay, because the whole idea is that only the terms here which survive are the ones which will be differentiated with respect to Aj, all the others will be 0, right. So this basically reduces to, and this has to be equal to 0 for extremization. Right, I am just taking the long one. Now, however, one of the things that you should understand is that Aj must be equal to n, j equal to 1 to all possible. So that means right. So this is the number of ensembles with energy level Ej. The probability that it is at that energy level is nothing but Aj divided by n, and you get exp minus . This is a probability that the system has energy Ej. Okay. And if you look at this expression, so this is clearly Pj from what we had derived previously, right? This one, correct? Yes or no? Except that I cheated by just writing this, one of the Lagrange multipliers as beta without proving it. There is no, I didn't provide an explicit proof and tell you that this beta is in fact the same beta which is 1 by kt, which occurs here and everywhere in thermodynamics, basically 1 by k times T. Okay. So the derivation, or to prove that it is possible, I am not going to go over the derivation now. Okay, it's a little a long derivation. It will take another one class to just do that. Instead, I am going to make the derivation and put it up in the notes, and you can actually take a look at it. Okay. So now we have this, and I told you that I will derive an expression for the Helmholtz free energy. So again, this again, Ej is nothing but can be written in terms of the Hamiltonian, in terms of Qi and Pi, like what we talked about in the last class. And now we want to talk about deriving the Helmholtz free energy. Before that, are there any quick questions? Yeah. Even above?
After applying Stirling's approximation, I think it
Yeah, yeah, yeah. Yes. So we'll do some thermodynamics now. What is the average internal energy of the system? What is the internal energy of the system at equilibrium? If I knew the probability that the system is at energy E, if I knew the probability of whatever the probability is for the system to be at energy EI, what would be the average internal energy of the system, or what was the internal energy of the system at equilibrium? That's it, right? Huh? It is the same as summation okay. Now what is Helmholtz free energy? What is the expression for Helmholtz free energy? Say Helmholtz free energy is A. Huh?
U minus Ts.
Yeah, right. U minus Ts, right? So which is correct, or like we do in thermodynamics, we can write dou A by dou T minus is equal to S, and obviously dou A by dou V is equal to P. Dou A by dou T, you are maintaining V constant and maintaining holding T constant. Of course, you will, if you are also considering the chemical potential of the system, you would continue to have a plus mu dn, no, not here, here, from here you would have a mu dn term, and therefore you have dou A by dou n, so you are keeping n constant here, and differentiated with respect to n at constant T, and V will be equal to the chemical potential of the system, right. So now we just want to show how this A turns out to be a function of P and Q. That is our goal here. So there are a couple of tricks that we have to use here in order to do that. So first we again write this A to be equal to U minus Ts, which implies the average energy or the internal energy of the system minus T times S, which is dou A by dou T is equal to A, right. Now, right. Now consider the expression so what does this turn out to be? Which is nothing but right. I have to do some manipulations. So just look at this expression here. Minus 1 by t square dou by dou t of a by t is nothing but this, using your basic calculus, which turns out to be a minus t into dou a by dou t, and which is nothing but u. Correct? Right. So u can also be written as minus t square dou by dou t of a by t, which can also be written as minus of 1 over t square of t, which is the same as, now dou of, what is dou of 1 by t? Minus 1 over t square dou t, right? So this term here becomes dou of which is also u. Okay. Any questions on that step? No. Now let's take a look at our energy, average energy of a system. This can be written as minus dou by dou beta summation over I exp minus beta times ei. Just take the derivative with respect to beta, ln of this quantity. I am saying that this u can also be written like this. So let us verify it. What happens? In the denominator you get I exp minus beta times ei, and in the numerator you have to differentiate the exponent function minus beta times ei, but then you have to differentiate it with respect to beta. So I would get a minus ei. Okay. Since there is a minus right in front of it already, it cancels with the minus that comes from this beta, and you get back exactly the same expression. Okay. So now we make a comparison between the two Any doubts? You have a doubt? It's okay? Okay. So make a comparison between these two expressions. So what should you get? It appears that a by t is proportional to your minus ln right, or a is equal to some constant, but that again that constant turns out to be the Boltzmann's constant times ln of I. Huh? Expression for the Helmholtz free energy. Now this is again, although this is just ei, this can be written as minus kBt ln of, or ln of the integral and for obvious reasons, if you are going to convert the, if you are going to consider the classical system, you need to be careful and have the quantity. What quantity should you have? H power 3n and n factorial should be present here if you are talking about a classical system. Okay. So we will leave it at this. We will leave it at this expression right here. This A is equal to minus kBt Qn, and this Qn or ln of Qn where Qn is equal to this and is called as a partition function. It will occur over and over again, so there is a name given to it. Okay. So now once you have your Helmholtz free energy, like I mentioned in the last class, once you have your Helmholtz free energy as a function of energy, or in other words as a function of the Hamiltonian, it becomes a function of the positions and the momenta. And if you have other quantities which are also functions of positions and momenta, you take appropriate derivatives to derive any thermodynamic quantity in terms of the positions and the momenta or the velocities of the system. Okay, that would be, and then you will have to properly average it if you are using statistical mechanics. However, if you are using molecular dynamic simulations, you would not do phase averaging, but rather you would do, what would you do? Time averaging. Okay, so with this I think we should stop with statistical mechanics and we should start doing introducing you to some molecular dynamics simulations. Okay.